But in this case, we do not have that. But anyhow, of course, these are only true in the generic case.
Yeah.
Otherwise, this already give a bound for the differential Null-Stalin set, right? If R is not to 0.
Right.
Yeah, because we have this, right? We have this. We will substitute, we will specialize this coefficient. If R is not 0, then we already have something.
But no Sternzatz is double exponential even in the linear case.
Pardon?
Effective differential no Sternzatz is double exponential even in the linear case.
Wow.
That's the problem basis, right?
Yeah, but that's also, again, that's a bound, right? That's not the best bound. Do you prove that's the best?
Well, it's a lower bound. There is a lower
In the
bound.
lower bound?
Yeah, it's showing double exponential.
I don't know that. I don't know that.
So
But
it can't be single exponential.
That means in many cases it is R. That's so let me check that, because if
It's double exponential in the number of okay. So I take it back. So you have one derivation.
Yeah.
So what I'm referring to is double exponential in the number of derivations.
Oh.
So in a single derivation, it's a different story.
that's maybe I think is a different. Maybe we are talking different things. I don't.
So again, when you have one derivation, it is.
You mean like the
One delta.
differential index, something like that.
Number of commuting derivations.
Yeah.
Like if you PD situation.
Ordinary and partial.
PD for equations. The lower bound is double exponential, the current best lower bound. Okay, so
But that's not contradictory to the result, because
No.
here, let's say S.
This is just.
you have only one derivation here, right?
Yeah.
So then in one derivation, the upper bound is
Well,
one can find a single exponential version.
whatever exponent to 1 is okay.
It's a single exponential in the rest of the data, what I'm saying. Number of determinants and polynomial in the degrees.
But let me say this: this kind of result does not give much insight to what we are talking about. What we are talking about is another problem, right?
Yeah.
In the algebraic case, when Brownell published his paper in Annals of Mathematics, is considered a breakthrough. So that's completely different. We are consider different things. Resultant cannot prove result.
But would you have you done some practical computations when you have some input system from someone wants to solve it and you run two algorithms in parallel? One is doing some elimination using the resultants, the other one is doing some characteristic sets.
No, I did not. As I said, I believe myself. From the starting, I believe this is a theoretical result, not.
Would you recommend it to anyone who wants to send?
No, I don't.
You don't recommend it.
No, I don't.
Waste of time to do the program.
So this is the typical algorithm that they use. Consider the worst case. Start with the worst case.
Right.
Yeah.
And that's why I don't recommend. So this, I believe this is somehow is.
Well, that's good to know.
This is the theoretical result. Anyway, we can say that under probability 1, we have a single exponential algorithm to eliminate n variables. This first time is done, I believe. Because this, we don't know single algorithm to eliminate n variables and differential variables. Somehow
would you explain again the what's inside of O? What is M?
M is the degree. Like a Bezout bound, like a Bezout.
Yes.
N is the variable. L is the number of terms, number of monomials inside the system. S is the order.
Okay, so I didn't read. So it's written. Church was saying this.
Yeah. So this result is somehow in certain way is nice because we have L is the size, number of the monomials, number of monomials. If you only have two monomials, so it's L is
Right.
2.
Yeah.
I see, but in general it's double exponential actually, the number of
Yeah. But that's the elegance of the theorem. You do not give the double L used to be L itself could be in the general case is already single double exponential or single exponential.
Yeah.
But here we use L. That's what we call intrinsic complexity, right?
Right, right.
What we know by intrinsic complexity, you do not give the number of variable and the degree. You use the exact the actual size. That's called intrinsic complexity.
But this is slightly misleading to someone who doesn't read the large small print underneath.
Of course, we do not claim we solve everything, but something is intrinsic. Here is the intrinsic complexity. But it's not bottom down intrinsic. In bottom down we need to even get rid of S. Something definite. The real size of that's what people do for. In algebraic case, people already give algorithm like that to give the intrinsic complexity to compute resultant or true form. But here we already have some intrinsic, but not all the way.
Oh, it's just the order.
Not all the way. Because we use Bezu. Bezu means the L is the size of Sparse. L is the size of Sparse.
Yeah, it's complicated too. First, you have to have the P0 through P, whatever.
PA.
And the problem with characteristic sets is then you first have to find a set of generators for the radical differential ideal, or
Yeah. But in this way we.
and then you get into business. I noticed the radical didn't appear in the definitions.
Here,
You see, the characteristic set method, it's harder to find the complexity. Precisely because what you just said.
That's a.
I mean, how do you relate?
Okay.
How do you relate the parameters in the characteristic set
Yeah,
to the given
right.
set? That's a hard part.
And then you run into the trouble when in Ritz anomaly, when it only applies to the general component, and not to. And he wanted to know what happens when you take the whole variety with all its components. So there's, but still, it's good to know the form, even the linear case.
For the difference case, we also worked out is something. Here I put a table to compare the differential case and difference case. For difference case, sometimes it's simpler, sometimes it's difficult. For the first definition, it's difficult because in the difference case, the corresponding to the difference case, we have one polynomial. But in the difference case, we might have more than one polynomial. But we guess it's one, but we cannot prove it. But for the criterion, the matrix M is quite complicated. But in the difference case, is very simple. It's only one variable. And for difference case, we have a matrix representation. That's something. But for difference case, we don't know. But the other, these are quite similar. These are homogeneity is quite similar, and these are degree are quite similar. Here is the exact. We know the exact degree. Order is all the same. So for difference case, we can somehow work it out. In certain cases it's easy, in certain cases it's more difficult. Anyway, I think I will go. I think YD already gave a talk here. Right. So I run it very quickly. And, the Chow form started with this Plicker coordinate of the lines in projective space. That's a Plicker coordinate, and the Grassmann coordinate, and the Chow jointly with Van der Waals. So these are trying to do the differential analog of all these. Try to extend this result to the differential variable. That's basically the result. Finally, we will done this. And let's I be a prime idea of dimension D, and we consider D plus 1 generic linear polynomials. UI the coefficient. Again, we use the intersection theorem, generic intersection theorem. We intersect this ideal. We intersect I with P0 to Pi, and then consider only the coefficient of Pi. And then we get one polynomial. This is always true, which is the prime dimension idea of codimension one. And this is defined with the Chow form. The Chow form basically is a polynomial of U0 and the UN. So each U is a set of n variables. So it's d plus 1 times n variables. So this is a differential Chow form. So let's say Chow form can be written in different ways. So the first property of Chow form is like somehow it's anti-symmetric for all the variables. It's quite homogeneous. It's quite uniform. So basically, all the variables appear inside. So the nice thing about Chow form is that order of Chow form is basically this is a definition of order of Chow form.
So the Chow form is dense.
It's just not dense, but it's very like dense. That's for example, if U00 is always inside.
Okay, it's just symmetric.
It's symmetric. The first one is anti-symmetric. The second one says something almost dense. Like for example, for all the variables, they have the same order.
Right.
So the first is the Chow form. Basically, the order of Chow form is the order for the ideal itself. So sometimes people use this to give definition. So it's also homogeneous, differentially homogeneous. So here we use degree. Since it's homogeneous, it's degree. It's homogeneous in each variable of UI. Each variable of UI. So the total degree is d plus 1 times r. So we call this the differential degree of I. So this is kind of like invariant. Of course, degree is not a birational, not even, but in very special cases, is a invariant of the variety of prime differential ideal. So remember that the algebraic degree is very common, but in differential case, I did not see anybody define degree for differential varieties. Maybe the first definition for degree. More interestingly, is another degree. Here again, using a Poisson product of Chow form. A Poisson product of Chow form can be written in a similar way with the resultant. Again, it can be written as a product of 1 to g of P0. P0 again is the linear. Now P0 is the linear polynomial P0.
So the Chow form is just a special case of the resultant.
The other way. The other way. That's P0, Pi. The other way. I will see that later. So P0 is basically a linear polynomial, so can be written as this. Here, something inside is very here I define G. I will write here. T0, that's the T0. It's basically the same. And all these points are generic points of the variety way. But importantly, here G is very important. So I will explain it here. So this is another invariant. So we know that in algebraic case, in a zero-dimensional case, a variety has a finite number of points, but for differential case, of course, everything is infinite. But here we give a finite number of elements. So let's say V. V is a irreducible differential variety of dimension d. So we intersect V with n generic linear polynomials. It becomes zero-dimensional, right? So we got a zero-dimensional variety, differential variety. But even zero-dimensional variety has an infinite number of solutions. Then we intersect it with some polynomial, not considered as polynomial, as algebraic primes. A, here's the definition of A0, A. Consider it as algebraic somehow, algebraic primes. Then these together, the only solution is this G point in the Poisson product. Then this number G is defined to be the leading differential degree of the variety.
Why do you put the binomial coefficient there?
You mean here?
In the algebraic primes? Second line.
Yeah, so that's when you do the differentiation n times the coefficient will appear.
Okay. That's those Leibniz rules. Okay.
That's this somehow we have a finite number of solutions to a set of differential polynomial. That's so that's somehow is important. Then this leading to the definition of differential Chow form, the Chow variety. So we need to for Chow variety is a special kind of moduli, right? So for Chow differential variety, we need an index because we can only define it for a class of varieties. So we give this index. N is very trivial. It's considered in the affine space of dimension n. D is these are all invariant. D is the dimension. Of course, this is a birational invariant. D, order H is also birational invariant. Maybe not. I don't know. I forgot. The leading degree T is and then M is the total differential degree. We have 4 invariant dimension, order, leading degree, and degree. Then with this we can define differential cycles like algebraic cycles. We can plus together Vi are irreducible variety of index dh, same index. With Si are integers, negative or positive, usually positive. Then the Chow form of V is just the product of the Chow form of Vi Fi, and the index of V is the dimension and order are the same, but the degree should be plus together.
So where is n?
Where is what?
N.
N is we consider all everything in the affine space of dimension n. That's the space. The space.
So we are to be
N is fixed.
any n.
Space.
Yeah, let's fix the space. Here's the definition. So a variety is called Chow variety. If we take a point from the variety, then we use this point as a coefficient of a polynomial. And if this polynomial can somehow become a Chow form of this index, n dh, because all these index, all these invariants come from the Chow form, so basically naturally can be defined. And from Chow form, Chow form corresponds to a cycle, to a differential cycle of this index. So this gives a one-to-one correspondence with all the differential cycles of this index with a point on a variety. So this is the extension of the somehow we parameterize all the differential varieties of this kind of course Chow coordinate. This is like a Breaker coordinate for lines. Basically, we extended this classic result to the differential case.
So that the first if and only if is not there. So
this is just a definition. That means
it's definition. But the second one is equivalence.
Yeah, the second one is what we proved. It can be proved somehow.
If there exists
Yeah, there exists.
No, I can't read it.
Which one? The definition?
I can't construe it. So, if there exists an AI and B? No, then it doesn't go.
No, for any.
For any AI.
If it's the notation.
Any point.
If it's a notation.
If it's a notation.
If A bar in V, he denote points in capital in the boldface V by AI bar.
If any point of V corresponds to a Chow form, and then
Any. Yeah, that's what I was saying.
Any.
AI and B is equivalent to knowing. There is a Chow form.
If any, yeah.
Yeah. Sorry.
But then we need to prove its existence. So our original paper, we proved only a very special case, only in G equal to 1. That's, the difficulty is to generalize it. We need to eliminate both differential and algebraic variables. Somehow we don't know how to do that.
Yeah.
But recently, Wiley, he's now visiting Berkeley with Scan. Somehow they prove the existence of differential Chow form. They use prolongation and these varieties and prolongation sequences to reduce the construction to algebraic case, and also to use something from model theory, definability of algebraic closed field. I not totally understand the paper, but somehow they prove it. You use other. So basically, we close this chapter by showing that the differential Chow form exists. So what's time?
Right now it's 5 minutes. Is there a model theory seminar?
Yes.
Yes.
Richard is
Oh, right. Yeah, so
I'll do use
maybe about 10 minutes.
another 5 minutes. Then
Another
we can
10
finish
minutes.
this
10 minutes, yeah. That gives us
very quickly.
half an hour to eat.
We could walk later on.
That's what we said. We try to connect Chow form with sparse result, and we have a set of monomials. So we define a map to map this. Basically, we consider all the values of these monomials, and then we take the image, and the image, the closure, the Toric closure, called the Toric, we call Toric variety. So basically, we can prove that this the differential resultant of this with that support is the differential Chow form of this variety. This variety can be proved the irreducible projective differential variety. That's we connect the two. So basically, sparse resultant is a Chow form of a Toric variety. That's the connection. And this is a very simple example. But unfortunately, in algebraic case, there are a lot of study of toric and everything. But in differential case, it's difficult because differential toric varieties is not binomial. It's not already binomial. But fortunately, I realized that in the difference case, it's binomial. So in difference case, I will skip this very quickly. In difference, I switch to difference case. Everything, Chow form in difference case can also be defined. But in difference case, we're using ZX lattice and instead of Z lattice. And then ZX lattice is basically ZX is the variable ZX module. The ZX module instead of the Z module. And then we can somehow extend almost all the result for binomial differential ideal to the difference case, not to differential case, because in differential case binomial ideal does not make any sense because we are make a differentiation. Binomial is not a binomial, but fortunately for difference that's true. The binomial I take a differentiation is still a binomial. So here, so we can consider binomial ideal. Binomial ideal is basically generated by binomial, sigma binomials. And I think I don't have time. So nicely that all kind of results can be extended. Actually not extended, we established this result because in the algebraic case, there's no such thing as like well mixed, perfect, reflexive. This is how new. Only the first case is already known. So basically, for in the long run case, the properties of a binomial ideal can be exactly described by his supporting lattice. That's basically everything. That means when doing binomial ideals, you do not need to do differential things. You just need to do a very simple lattice, very simple module, CX module. Then these are toric variety. So again, quite similar. The toric variety, basically the image, the coin, here is the coin. Here is a concurrent of the image of a set of monomial. Basically, everything the same. So here I can prove that a sigma variety is toric, if and only if it's a defining variety is toric. Toric is toric ideal, toric sigma ideal definition. It's a binomial ideal, very, very simple binomial ideal. It's prime, it's reflexive, and even more. So these are like a similar result with here the algorithms are real. We can do real algorithm. We can do real computation. We can also know the coordinate ring of a toric variety. It's something like we call it affine NX module. And also, it can be considered as a group action. So, a toric variety, the toric even only if it contains the sigma torus as an open subset, and then with the group action on T0, and then these are like similar extensions of the algebraic result. Here's a summary. So we consider 3 subject differential. I spend most of my time on sparse resultant, and then Chow form, and then toric varieties, and this connect toric varieties connect resultant and Chow form. Thank you. I think the papers, most of the papers are published.
In your sections on difference varieties, are you following Richard Cohn's development or Hrushevsky's, or which development of do you define difference variety, or do you assume
we define, but
you define it? Okay.
We try to use a little bit modern approach, like
for example.
Hrushevsky's, we use some of his results, but not really not really the deep one. We use there's a recent lecture notes by Webermer. I think he read clearly.
Yes.
He read it very clearly.
Yes.
We try to use
good.
that one. We try to use
Yeah, thank you.
It's modern, but not elementary part.
Very clear. Yeah.
The first 4 papers are the first one
have
is
this.
sparse differential result, and then the sparse difference result, and all appears this year, and Chow form this appeared like several years ago.
Yeah.
And,
Okay.
difference Chow form is worked by Wiley and one of her students. I did not draw, and then the binomial idea is not published yet.
Are you going to give William your slides?
Yes.
Good. Thank you.
All right, now we thank the speaker one more.
Okay.
Will there be any